they set or use the type of service field themselves. They don't let end users or end hosts actually set it. Implications of fragmentation, I think we kind of covered this. If you send packets that are too large, that are larger than the MTU, with IPv4 we know that the router has to fragment it, which means the router has additional work to do. So one way to actually attack a router is to send a lot of packets that are larger than the MTU and force the router to do a lot of work. Security IP options as well, I think similar attack. IP options, as Rob mentioned, require additional processing at the router. Often this is done at the control plane of the router, or what we call the slow path. And so again, if you want to try and attack a router, send it packets with a lot of options, and the router, you're using more of the CPU resources at that router. And again, this is the reason why many routers will either ignore packets options or they'll just altogether drop packets that have options in them. Implications of the TTL, we covered this already. It allows discovery of the topology. This is actually what traceroute exploits. This is arguable. Some of us think traceroute is a great tool that you can use to discover your network topology. Some operators think it's a terrible tool because it allows others to discover their topology. Which side of that argument you come down on, accordingly operators will configure their routers. If you run traceroute, you'll often see that it doesn't make it, that there are some routers along the way that don't respond. It's because those operators have configured their routers to not respond to TTL exceeded messages. So you can start to see a pattern here of fields that had security vulnerabilities and operators have responded by disabling them. I could not think of any problem with the protocol field or the checksum field. If you come up with it with an attack, let me know. There's always surprising things. But that aside, I think those were all the security issues I could think that are notable and people have come up with. Any other thoughts on security before I move on? Okay, so with that, recap the IP header design. I hope you feel like it's actually more nuanced than it first seems. It's very easy to look at the IP header and sort of walk through the fields and just say, okay, check, 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 I get it. There's actually a fair amount of careful thought that goes into what is in that header versus not and why. And all of this comes from, you're actually juggling multiple goals. You want an efficient implementation. You want it to be secure. And importantly, you also want to design in some ability to evolve to meet future needs. The IPv4 header did a reasonable job at many of these. I think the IPv6 header does a slightly better job. Security is the one area where there's still clearly a hole. With that, any questions? We are leaving the network layer otherwise. Okay. So with that next topic, we're moving up a layer. We're going to the transport layer in L4. And we're going to start talking first about reliability and how do we implement reliability at that layer. Today's lecture, we're going to cover the basic concepts and mechanisms. The next lecture, we're going to talk about TCP and the protocol details. This is very similar to how we did BGP or how we did routing. We're first going to get the basic concepts. Then we're going to assemble it into a protocol. This material is not on the midterm. Please don't leave the class right away. I will cry or something. So sit through it. It's actually useful for project 2, and it's going to be critical for understanding TCP. So just basics. Why do we need reliability? I hope this is pretty obvious to everyone. If you're going to transfer a file on the internet, you want to know you got the file. You got it correctly. You got it in its entirety. Right? So we need reliable transfer. The challenge is how we're going to build this on top of a buggy network or best effort network. And so this is really an exercise in trying to reconcile kind of application abstractions. What is it that application developers want as an abstraction when they're building applications versus what are the abstractions that we can easily support in the network, right? And we've already said we're going to do a best effort. So quick recap of things we've said in the past about reliability. We've said that reliability is the job of the end host, not the network, right? And we went through this whole exercise with the end-to-end principle that led us to conclude that we want reliability implemented at the end host. We also said that we were going to do reliability at the transport layer, and that's implemented in the operating system. And the argument for why we're doing it there is one of convenience. Otherwise, every application would have to implement what we're about to discuss for the next 2 lectures. Right? How do you actually rebuild reliable transfer on top of an unreliable network? So with that, what are the semantics of correct delivery? At the network layer, we've said the semantics we're shooting for are best effort delivery. Packet may or may not be delivered. What you're going to see is that at the transport layer, the delivery semantics we're going to support are what we call at least once delivery. So at the transport layer, the receiver is going to receive every packet at least once. It might receive the same packet more than once. And you're going to see this is kind of fundamentally the model we have to live with given a best effort network underneath. And then later when we get to things like HTTP and the application layer on top of TCP, you're going to get exactly once delivery. So when I reliably transfer file A from point A to point B, at the application layer, it gets to just think that the entire file was delivered exactly once and reliably delivered. The transport layer sitting underneath it is going to see certain packets or bits of that file multiple times, maybe. And it's going to have to learn to deal with that. Okay? So goals for reliable transfer, anytime we start our design, first we talk about the goals. So correctness, which is what we just covered, which is that the destination receives every packet uncorrupted at least once. Okay? That's our correctness goal for the transport layer. What else would we want as goals from a reliable transport? So I'm transferring a bunch of packets or file from point A to point B. I want it correctly transferred. What else do I want? Yep. So timeliness, right? No one wants to sit around waiting forever for the packets to arrive. What else? Efficiency, that's the last one. Okay. I could implement reliability by sending every packet 10 times. That might even be pretty quick. It would probably do the job. It's not a very good use of bandwidth, right, to just say I'm going to consume 10 times more than I need. So we would like to avoid sending packets unnecessarily. One thing to note, our correctness condition said at least once, but there is never a guarantee on the internet that you will for sure reliably transfer a file or reliably deliver a packet. Right? There is always the possibility that the sender cannot reasonably deliver the packet. An extreme example would be if your network is partitioned. You have no path to the destination. Right? So it's totally valid behavior for a reliability protocol to say, I've tried enough, I'm giving up. I could not transfer this packet. The only thing that we ask in that case is that the sender, transport layer, the sender side, has to tell the application, I failed. This transfer failed. And under no circumstance should that transport layer implementation say, I succeeded in delivering the file when it actually failed. Okay. So it's okay to fail, but you should know that you failed. So with that, best effort network, just to enumerate all the things that could go wrong. We said packets can be lost. We said they could be corrupted. They can be reordered. In case you've forgotten, let's say I was sending packet 1 and followed by packet 2, and then I had a route change, and packet 2 actually got to take a path that was faster than the one packet 1 was taking. So it's acceptable for packet 2 to arrive before packet 1 at the receiver. Packets can be delayed. We've talked about queues, packets sitting in queues and incurring queuing delay, and packets can be duplicated. So it is actually possible for the network to generate an unnecessary copy of a packet, and we'll get to that in a minute. These are all the things that can go wrong. These are all the things that our reliability protocol is going to have to fix. Okay, so the way we're going to talk about as we develop the protocol, just a quick reminder of these kinds of diagrams where we have time going down, and we send packets from a sender to a receiver. They're going down in time and coming back to the receiver. Half of that is the one-way delay from sender to receiver. The time for the packet to go and come, some kind of response to come back to the sender is what we call the round-trip time, or the RTT. Okay, we're going to be using this as we go, yep. Not in what we're doing. So we would say it's the time from when the last bit went left to when the first bit came. But we're also not doing these kind of microscopic calculations in here. Yep.
Would the one-way delay be different, like coming inside from sender to receiver?
Yes, it could. So there's no reason why your one-way delay has to be exactly half your round-trip time. In all the examples we'll be doing here, yes. But on the internet, end-to-end, no, you're right. And we talked about this with BGP, that paths could be asymmetric, for example. Any other questions? Okay, so let's get started designing a reliability protocol. And we're going to start with a single packet. This is very simple, but it actually highlights most of the building blocks we're going to need. So let's step through it fairly slowly. So remember, these are all the bad things that can happen to a packet. And we're going to say we have a sender here that's trying to send a packet to the receiver. And the packet gets dropped. Okay, the packet got lost. What should the sender do? We've seen this already in a different context. Yeah, set a timer, right? So the sender is going to start a timer when it sends the packet. After some amount of time, if it's not heard anything back from the receiver, it's going to time out, or the timer will expire, and it's going to resend the packet. It's going to keep doing this. So the receiver, when it receives the packet, is going to send back what we call an acknowledgement, saying, I got the packet. When the acknowledgement reaches the sender is going to cancel its timer. Okay? This is kind of the very basic mechanism. Are we good with this? Yeah. What if the ACK got dropped? Do I need to do anything more than that? No, right? I just had a timer, I timed out, I sent the packet over, and this time it made it through, the ACK comes back, the sender is happy. So we reliably delivered the packet, but notice the receiver received the packet twice. This is fundamental. Can you think of a way we could have avoided having the receiver see the packet twice? You actually can't, because there's no way for the sender to be able to distinguish between the packet was lost versus the ACK was lost. So the sender has to retransmit. The receiver is going to see it twice. This is not going to worry us. This is correct. By our goals of at least once delivery, we got it there at least once. We got it twice, but that's fine. Okay? This brings up the question of how do we set timers. Right? If your timer is too long, you're going to delay delivery. Right? You're going to wait too long to retransmit. If your timer is too short, you're going to unnecessarily send multiple packets when you didn't need to. Ideally, what kind of timer do we want? Order what time scale? What roughly would be a good timeout value? Yep. The same as your RTT. So ideally, your timeout should be proportional to your round trip time. In practice, this is actually not trivial to get right, and we're going to talk about this when we talk about how TCP does this, because your round trip time can be anywhere from 10 microseconds to hundreds of milliseconds. So you have many orders of magnitude differences in your path. Right? So if you set it wrong, you could be 10,000 times slower than you need it to be, for example. So we're going to have to learn that RTT. Also, it varies in time, depending on what the load on the network was, whether your packet was in a queue or not, for how long it was in the queue, and so on. So actually estimating a good timeout is a non-trivial question. In practice, your timeout is what you would, if all else has failed, then you will take a timeout. But you're never happy to actually have a timeout. We're going to try and work pretty hard to not have to rely on timeouts. But so with that, we now know how to deal with packets or ACKs that get lost. Okay? How about packets that get corrupted? So now I sent this packet along, a few bits got flipped along the way. What are we going to do to deal with that? Again, we've seen the mechanism for this before. Yep. So we had this checksum. So we're now going to compute a checksum at the destination, make sure that it matches what the packet sent. This is not the same as the IPv4 header checksum. Remember, that checksum was just over the header. We now need a checksum over the entire contents of the packet. Right? We're checking whether the file was actually correctly transferred. So we're going to need a checksum that covers the payload. If the checksum fails, you could send back feedback to the sender saying, this is a negative acknowledgement. You sent me a bad packet. We call that a NAC for negative acknowledgement. And then the sender can resend the packet. Assuming it made it through this time, you would correctly transfer. Okay? Is there something else you could have done instead of sending a NAC? Yeah, just do nothing. Just drop the packet. And exactly the same mechanism we talked about with timeouts will work. So if you believe that bit errors corruption is very, very rare and you don't